Okay, next we have the spin quantum number, and spin quantum number is represented by this symbol S. Now the idea of spin was first time introduced by two scientists. One is Uhlenbeck and the second scientist was Goodsmith. And they give this idea in 1925. And they give this idea of spin to explain the fine structure of, for the explanation of fine structure of hydrogen-like atoms, and for the explanation of anomalous Zeeman effect. Zeeman effect. And the spin of electron can take a fixed value. Spin of electron can take fixed value, which is 1 over 2. Now if the spin is up, then we have 1 over 2. If the spin is down, then we have minus 1 over 2. And the magnitude of spin angular momentum, the magnitude of spin angular momentum with spin quantum number S is given by, this is the magnitude of spin quantum number, spin angular momentum, or we can write it as like this, which is equal to S into S plus 1 square root into h bar. This is the third quantum number we discussed so far. The fourth quantum number is the total quantum number. The fourth one is the total quantum number. The total angular momentum, which I represent by this symbol capital J, is equal to the sum of orbital angular momentum and spin angular momentum. This is the total angular momentum, which is the sum of orbital angular momentum and spin angular momentum. And the magnitude of this total angular momentum is, we represent the magnitude by this symbol or just J, which is equal to J into J plus 1 square root into h bar, where this J, this small j, where J is called total quantum number. This is called total quantum number, and which can have values J has values started from L plus S, L plus S minus 1. These are the orbital quantum number and this is the spin quantum number. So J has values started from L plus S minus 1 up to L minus S. So this is total quantum number. Now to explain the splitting of spectral line in magnetic field, like to explain the Zeeman effect, we introduce 3 more quantum numbers, and they are called magnetic quantum numbers, which I will discuss here. The fifth one is the magnetic orbital quantum number. We call it the magnetic orbital quantum number. And we will represent it by this symbol m with subscript l, ml. Now suppose we have an electron orbiting in an elliptical orbit. Suppose we have an electron, I will use a different colorful point here. Suppose we have an electron which is orbiting in an elliptical orbit, and the motion of the electron is anticlockwise. This is electron moving in this elliptical orbit in anticlockwise direction. Now if we suppose this is my x-axis and this is my z-axis, suppose we had applied a magnetic field, external magnetic field, in the z direction, z-axis, along z-axis. Now the orbital angular momentum direction of this electron, which is moving anticlockwise, is normal to this plane of this orbit. So the direction of orbital angular momentum is this one. It's normal, means perpendicular to this plane. This is the direction of orbital angular momentum, L. Now the angle between this magnetic field, this is the magnetic field, and this orbital angular momentum is theta, let's suppose. Now this angular momentum persists around the magnetic field. It persists around the magnetic field. It persists around the magnetic field like the spinning of a mechanical top in the gravitational field. So this is the precision of this orbital angular momentum. So the precision is like a mechanical top in the gravitational magnetic field. If you rotate a top by using your finger, then this top will move like this. So it's also precise about its axis, which is perpendicular to the top. So it's always moved like this. Similarly, this angular momentum also persists around this magnetic field. Once the atoms is placed in a external magnetic field, and the rate of this precision, how fast it is moving, depends on the strain of the magnetic field. Greater the magnetic field, greater will be the precision, and smaller the magnetic field, smaller will be the precision. Now if I take a projection of this orbital angular momentum in the direction of magnetic field, and the projection is, let's suppose I focus a light here and I take the projection of this orbital angular momentum vector in the direction of magnetic field. Let's suppose this is the projection. The projection is now this one. This is the projection now. and this projection of orbital angular momentum on the magnetic field direction we represented by ml, and this projection is called magnetic orbital quantum number. So I can say that the projection of orbital angular momentum L, orbital angular momentum vector L on the magnetic field direction is called magnetic orbital quantum number. And we represented by this symbol ML. And this ML can take values its values are ML, which are L, L minus 1, L minus 2, we have 0, then we have 1, 2, and up to minus L. This is the value of this magnetic orbital quantum number. So overall we can say that there are 2L plus 1 possible values. For a given L. Possible values of this magnetic orbital quantum number for a given L. For example, if I say that if L is equal to 0, L has, this ML has only one value, which is 1. Which is, if L is equal to 1, which is 0, yes, which is 0. Now, for L is equal to, let's say we have 1, ML has 3 values. ML has 3 values, one is 1, one is 0, and the other one is minus 1. So total we have 2L plus 1 values, which are 3. Because L is equal to 1, so 2 and 1 is 2 plus 1 is, which is equal to 3. For L is equal to 2, ML has 5 values, which are 2, 1, 0, minus 1, 2. Because we can calculate now the number of values of ML by using this formula 2L plus 1, which is 2 times L is 2 plus 1, which is equal to 5 values, and so on. Now, the angle between this orbital angular momentum and this magnetic orbital quantum number and this orbital angular momentum is, we calculated by using this formula cos of theta, which is equal to, this is cos of theta, this is the perpendicular, this is the base, and this is the hypotenuse. Base we have ML and hypotenuse we have L. So it means that ml is equal to L cos theta. Now here I will take an example. Suppose that for L is equal to 3, the permitted orientation of L are 7. The permitted orientation of L are 7. 7 orientations, permitted orientation of L are possible, for which if L is equal to 3, then ML has how many values? ML has 2L plus 1 values. 2 into 3 plus 1, which is equal to 7 values. And ML has 7 values, which are 3, 2, minus 1, 0, 1, 2, 3. Now we will calculate the, we will define the permitted orientations now. Suppose this is the magnetic field direction, okay. So we have 3, 2, 1, 0, minus 1, minus 2, minus 3. So the permitted orientation of LR, we have 0. So L has one direction is this one orientation of L is possible orientation is this one, the other one is this one, the third one is this one, the fourth one is this one, the fifth one is this one, the sixth one is this one, and the seventh one is this one. These are the possible permitted orientation of L, because L is precise around the magnetic field. So it's either precise around in this way, or it's either precise in this way, or it's 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 precise in this way, and or it's precise in this way. These are the possible 7 orientation of L. So the 7 directions are shown here. Here we have 3, this is 2, this is 1, this is 0, this is minus 1, this is minus 2, and this is minus 3. So the first orientation 3, 2, 1, 0, minus 1, minus 2, minus 3. These are the 7 possible orientation of this orbital angular momentum once there is an external magnetic field. This is the magnetic field direction B. So it means that L cannot be inclined to B at any other angle apart from this. I can write it here. L cannot be inclined to B, to the external magnetic field B, at any other angle. And this is called space quantization. So this is all about magnetic orbital quantum number. So the other 2 quantum numbers, which are magnetic spin quantum number and magnetic total angular momentum quantum number, I will discuss in the next video. Thank you.